sucks. Oh, and then Spanish. Thank you for reminding me.
Spanish sucks.
Spanish 3.
I only passed. Why would you pass that?
I don't know.
How did you do that
to
yourself?
Spanish 2 was kind of a blur last year. Like, it was just there.
See, that's one of these things about this true block. I think like Spanish is really hard because I mean you haven't had it for so long versus having it like every other day. I think that's. Okay, so going back, I mean, when I was going back through these sections, I kind of like redid that this chapter. So like the velocity versus time graph, and talking about like this is where we started talking about like, bless you, the area like under a curve, because that area is the total time traveled or the total distance traveled, sorry. So, but also looking at a graph like this, just making sure we understand like exactly what's going on here. So velocity versus time graph. So the question is like kind of thinking about what's happening from 9 to 10 a.m. in this, I guess it's a train. So thinking about velocity at 8 a.m. it's at 0. So that means it's not going anywhere. Velocity is how fast it's going. And so it's increasing its speed until 9 a.m. and then at 9 a.m. what happens?
Stops. Or it goes steady.
It goes steady. It's a constant speed. So it didn't stop. Yep, so it's good to notice that. It didn't stop. It just at a constant speed. So like the train gets itself going and maybe a train takes longer to get going than other vehicles. I don't know, that it increases its speed for a whole hour. And then it's steady for another hour. So it's, or ish. I guess it's not about ish. So it's steady for a while, that it's at a constant speed there. So it's still traveling forward, just at a steady rate. So it's going like, I don't know, is that like 30 miles an hour for that amount of time? And maybe that's like initially like getting out of the station or whatever, and then they're at a constant speed, and then maybe they're like out in the country or like going like there's some place where they can increase their speed, so longer straightaway or something like that. So from 12 to 1, what's happening? It's decreasing, so it's slowing down. So for the last like hour-ish, the train is slowing down until it gets down to 0. So we can actually see quite a bit from this graph. So it does eventually get down to 0, so it stops at 1 o'clock. So that talks about the speed and what's happening. And then asks how far did the train travel during this whole time? And remember, this is where we talk about that area under the curve. So or the area under our line here. So we can figure out the distance traveled when we figure that out, those pieces. So we can kind of break this up into sections, and you can kind of do approximate. Don't let yourself get too like bent out of shape about are we exactly at 9 or 10 or whatever. We're going to try to do our best here to make an estimate. I don't know if you guys can see it better on yours, but. Well, I'd say definitely 12 to 1 is across the bottom is a 1. Now, you guys did triangles and rectangles? Is that what you want to do? You could do trapezoids, but I think triangles and rectangles are just as easy. This looks like it's going about 50 here, right? So this, we have to do the area of this triangle, so 1/2 base times height. So this little section, you'd be going 25 miles where it's decreasing. And I don't know, what do you think? Is that 10? Let's call that 10, right? Make that easier on ourselves. So across the bottom, let's go 2. This is 50. So this one is 100. Should we call that like 930? That one one we have to do a trapezoid, huh? Looks that way. Let's skip that one for now. So here, let's go 1, and then this is up about 30, I'm going to call it. So this is about 15. Base times height divided by 2. I'm going to call this 0.5 across the bottom. Base times height, because that's a rectangle there. So this is also 15. And then here, this is 0.5. This is 30. So the area of a trapezoid, you do base 1 plus base 2, divide by 2 times the height. So we get 30 and 50 is 80. Divide by 2 is 40 times 0.5 is going to be 20 there, I think, right? And then we just add up all those areas. That's that summation. And again, this is an estimate. So if you're like, oh, I called that, you know, I estimated that to be like, you know, 1/4 of an hour or something like that, or I put that at the whole value. We just add up all those areas to find our distance. And so again, it's not a perfect science. So if you got something slightly different from us, you're probably still okay, because you're probably still in that ballpark. It looks like about 175 miles. But again, hopefully you're something close to that depending on how you guys broke things up. It's probably something similar to that. All right, so that's what we did in 13.1. We talked about the distance versus time and just kind of understanding that area under a curve or like under a line and how that's important. So our next one is when we talked about right and left-hand endpoints. Now this one's definitely a more approximate value because this doesn't have those straight lines or those perfect lines like we had before. This is where we're going to make the rectangles. So when they talk about a right-hand endpoint, they're talking about rectangles. And again, this is approximating the area. So you have to be okay with this isn't a very good estimate in this case. And we can talk about that because one of them is probably going to be better than the other or slightly better, right hand versus left hand. But then some of you guys might be already thinking ahead to what we can do later where you're like, oh, that looks more like a trapezoid or that looks more like a triangle. If they're asking us to use right hand or left hand endpoint, they're asking us to use rectangles. So kind of trying to keep the like now that we know how to do other things, sometimes that makes some of these a little bit tougher. Sorry, I actually took a picture of this one because the graph wasn't showing up, and I know the one time I think you guys were mad at me for not having lines on the graph. So when I was scanning it, it wasn't showing up. So we're going to do right hand endpoint and then left hand endpoint. So right hand is going to go on the right side of the graph and make little rectangles out of this. Go up high enough on that one. So take a minute to see if you guys So again, just like the one above, we're just doing base times height. These are just little rectangles, and just trying to make a estimation. So it's 1 by 1 for this first one. The next one, I think it goes up to like 2.5 or 2 1/4. I'll probably just go 2.5, right? So it doesn't quite go through like at an intersection on the right side there. This next one goes up to 3 by 1. And then this one only goes up to 1. It's a little bit shorter there. So this right-hand endpoint is going to give us about a 7.5 if I add those all up. Then switching us over to the left-hand endpoint, I don't remember, I think they end up being pretty close because the graph isn't very different, but I don't think they're the same though. And then sometimes I'll, like if you need to sketch another graph, otherwise hopefully you can visualize it with me here. So this time I'm going on the left side. So this one over here. High on that one, right? So this one ends up being a 2. This is a 1. This one's 2.5. And then this one's 3. So the left-hand endpoint is my upper one, and then my right-hand endpoint is going to be my lower one. So they give me, two different outcomes, because what is that? Is this one 8.5?
Yeah.
Thanks. So 8.5, and what we learned was the actual answer is somewhere in the middle between those. And as we approach the limit between those two, like we get closer and closer, the actual answer is somewhere between those two, or that we go upper versus lower. We're going too high on this one, going too low. We started to learn that we can figure out kind of the in-between. All right, so when you guys are ready, you guys can flip the page over. Now this one is the one where we actually had it, we're trying to find as specific as an area as we can. And what these end up doing is they end up looking like shapes that we recognize as something we can find the area of. So I did give you guys little graphs there. You could probably do these without any graph paper, but I thought, I know some of you guys like the formality of graphs, that's fine. And we're going to graph these using this information, and then we're going to look for that area under the curve. So on the homework, I do specifically tell you guys to use this method. If you guys look at the bottom of the page, it says 4 through 7 all use the method from this section. So on numbers 4 through 7, you're going to use this method, and I'll try to make sure that's clear to you guys when we test. If this is the method. This is kind of the long way. So I think we talked about that. There's a long way and a short way for a lot of this stuff. This is kind of the long way with it. Now, this one goes from 4 to 12. That's what it's telling me to do. So on my graph, I didn't put an axis because I wanted you guys to be able to determine how you guys wanted to do this. So 4, I would put here. I think I should be able to fit it 5, 6, 7, 8, 9, 10, 11, 12, yeah. So 4 to 12, I'm going to put my graph, and now I could go all the way back to the axis. We're so used to graphing in slope-intercept form, starting at 6 and going up 1 over 4. However, if I know 4, I can put 4 in and figure out what my y value would be. So I'm going to put 4 in. So 4 times 4 is 1, plus 6 would be 7. So that's what this is going to start at. And I know this is a linear graph, so I know it goes up 1 over 4. And so if I want to, at this point, use my slope, I can. I don't have to find every value in between there because I can use the fact that I have a slope there. So up 1 over 4. I go too far over. Up 1 over 4. So now I realize we need to go all the way back down to the axis. So this is my line, and I want the area under this curve, or under this line, I guess. It's not a curve. Sorry, my after break brain is not as strong as. So we need to go all the way back down to 0. So we need all of this area all the way back down to 0. But hopefully we're able to figure that out even without seeing the bottom half of the graph. You guys have space, you could probably actually maybe go down to 0. This is technically a trapezoid, right? So if I go straight down to 0, this is going to be a trapezoid. It would go all the way down here. It would look something like this if I actually graphed it in a normal graph, right? So if a trapezoid, I do base 1 plus base 2 divided by 2 times the height. The bases are these. And then the height's going to be across the bottom down there. So what's base 1 going to be? Just going to be 7. It went up to 7 was like the highest. It went on this side. So that's going to be 7. What's base 2 going to be? 9. It goes up to 9 over here because it went up 1 over 4. Divide by 2 times the height. What's the height going to be? Yeah, it's from 4 to 12, so that's how high it would actually be. So the trapezoid is kind of set on its side, so that makes it a little bit confusing. So 7 plus 9 is 16, divided by 2 is 8, times 8 again would be 64, right? So again, this is considered the long way, and so this would be part B, 64. Part A is drawing the graph, part B would be the answer 64. Now this next one is 6 is our integral, like we're finding the integral of 6. So like, what kind of line is like y equals 6? It's just a straight flat line at 6. So in this case, we're going from negative 5 to negative 2. So that's negative 3, negative 2. And so let's, we should probably make this 0. We're going up to 6. And so our graph in this case is just a rectangle. So flat line at 6, but it only goes from negative 5 to negative 2. So it's a little bit easier to like understand kind of what's going on here. Again, I didn't put the axes on here to not be confusing, but maybe that is confusing not having them there. So it's that whole space, so that's just a rectangle. So it's 6 times our base, which is, it's 3 across, the difference between those two. So again, our graph and our approximate area there, or our exact area. Now our last one, we talked about one like this before, and hopefully you remember what this should look like. Now we're going from negative 3 to positive 3. And this might be another one. You can either grab your graphing calculator, or it might be worth just like substituting values in, kind of like we did, because the numbers actually work out pretty nice. Stupid smart notebook logo here that's killing me here. All right, so from negative 3, so if I put negative 3 in, negative 3 squared is going to be 9. 9 minus 9 is 0. So negative 3, it's going to be at 0. And then actually at positive 3, it's going to be at 0 again. Because when you square it, it doesn't matter if it's positive or negative. So let me switch this over here. I'll put this on the graph. So negative 3, 0. So at negative 3, we're going to be at 0. I'm going to put it here for my 0. Positive 3, we're at 0. When I put 0 in, I do 0 squared is 0. 9 minus 0 is 9. Square root of 9 is 3. What's the shape of this graph going to look like? Do you guys remember? It's like a semicircle, yeah, it's a half circle here. So essentially what I have going on here should be like that. And if you forgot that again, that might be something worth like throwing that in your graphing calculator, seeing what that looks like. The way we know it's not a straight line is just, well, first of all, hopefully the fact that it has a different equation to it. But if you put 1 or 2 in, you would get a decimal, I believe. No? Yeah, you will. Just because of the way the numbers work out. So if you didn't realize it was a circle, just know that, start realizing that the square root might actually have kind of a half circle shape to it. So we need to find the area of our half circle. So area of a circle is pi r squared. But since we're only taking half the circle, we're going to take half of that area. Now the radius in this case, here's the center, it just goes out 3 in every direction. So the radius is 3. So you could leave it that way, kind of a nice way to write it. You could call that 4.5 pi. You could figure out what 4.5 pi is, which is about 14.14 or something. Okay. So again, this is considered the long way how to do finding the area under a curve. What we learned next was these integrals, and this was that antiderivative. And so this might take a little bit of like cobweb, like cleaning off, like to do at first, because initially when I was looking at it, I was like, wait, what did we do again here? Because this is not something that is super intuitive to begin with. Remember, we're doing the opposite of finding the derivative. So, if you guys recall, we take the power and we add 1 to it. So this becomes an x to the third. But then whatever that number is, you have to put that one on the bottom. So I raise the power by 1 and divide it by that power. And do the same thing in this next part. Raise the power by 1, so it's become x squared, but then divide by the power. And I'll simplify this. And remember, this is like 5x to the 0. So I'm going to raise the power by 1, so it becomes x to the first, but then I'm going to divide by that power. So if you forgot how to do this, totally okay. Like again, it took a little bit of like, last night I was like, what in the world? What did we do here? Like trying to remember how to do this. But now I gave you nice numbers in this case. These all simplify pretty nicely. Because of the numbers that we had as our coefficients. So remember, if we wanted to find that antiderivative or the value of the integral or the equation for the integral, we'd write it this way. The plus c just means that there could be a constant there. If we were trying to find the derivative of it, that constant would go away. You don't have to worry about the plus c right now. But what we do now is we basically figure out, you know, like this part from 0 to 5. But we subtract it. So we're going to figure out what this is from at 5, and then figure out 0. 0 is nice because it's just 0. So we're going to substitute 5 into just this part of the equation. We don't have to worry about the c. So we're going to put 5 in here. So rather than having to do the area under the curve, this allows us to skip that. And again, the 0, you normally would subtract that second half, which I'll show you guys in a second, but that's just going to be 0. So I got 150, is that what you guys got? And again, it's really subtracting 0, because if you put 0 into all those terms, it ends up just being 0. When it goes from 0 to 5, anytime 0 is your starting point, it's kind of a nice one with these integrals. So that being said, it takes us to number 2 here, where that's not going to be quite as nice. So first find that antiderivative. I'll give you guys a minute to try that. And then you're finding basically from 4 to -2, but you're going to subtract the difference between them. All right, so remember, raise the power by 1, divide by that number. So raising the power by 1, I get x to the 3rd. Then when I divide that by 3, so this will just be x to the 3rd as my first term. Raise the power by 1, this becomes x squared, but then I have to divide the 8 by 2, so this ends up being 4. Hopefully that's what you guys got. So then what we have to basically do is do that from 4 to -2. So I'm going to do 4 to the 3rd minus 4 times 4 squared minus this whole thing, -2 to the 3rd minus 4 times -2 squared. So just be careful that maybe doing these in pieces is sometimes a good idea, like figuring out each part of it and then subtracting them. So that's 0, right? That first half, I think. And I believe this is a -24. What you guys got? Do you get 24 for the whole thing?
Yeah.
Okay. So this is considered our short way, where we didn't actually have to go then and find that area under that curve. Okay, so just make sure you guys are following my direction on that 4 through 7 all piece, that you're realizing that you should be doing that. So this one, the 4 through 7 all, use the method from 13.3. That's where you actually like graph it and see what that area looks like. If you need graph paper, I do have some, so let me know if you ever, otherwise you can probably sketch it pretty well.